Good morning. My name is Marco Antonio Paredes. I'm a PhD candidate in engineering sciences. It is a pleasure to share with you the topic analyzing the relationship between pore, evolution, and failure behavior of Inconel parts additively manufactured. I would like to talk about introduction. Laser powder bed fusion (LPBF) enables the fabrication of complex Inconel 718 components wherever process-induced porosity may reduce their mechanical performance. X-ray computed tomography (CT) provides a non-destructive technique for three-dimensional characterization of internal defects before mechanical testing. This work aims to investigate the influence of room temperature 22 degrees Celsius, high temperature tensile loading 615 degrees Celsius, and creep conditions 650 degrees Celsius on the deformation and failure of as-built LPBF Inconel 718. Scanning electron microscope was used to correlate the fracture mechanisms with the initial pore morphology identified by CT. Now, I would like to talk about materials and methods. The superalloy Inconel 718 was chosen. The LPBF technique was used to obtain bars printed at 0 degrees with dimension of 112 by 28 by 16 millimeters. From these printing bars, ASTM E8 specimens were manufactured with the EDN machine. Sample of 2 by 2 by 2.5 millimeters are cured using a diamond cutter, which is used for characterization by means of CT. Chemical testing tests were then performed at room temperature, tensile test at 650 degrees Celsius, and finally, a creep test at 650 degrees Celsius. Each of the mechanical testing sample was then characterized by CT. Fractograph of Inconel 718 were obtained using a scanning electron microscope. The specimens were using a microtomograph 160 kilovolts and 800 images with an exposure time of 2 seconds to acquire a volume with a resolution of 3 cubic micrometers. From of this volume, the porosity analysis is carried out. Results: isolated pores with size lower than 80 micrometers were obtained of CT porosity distribution for AP. A stress strain cure was carried out at 22 degrees Celsius, obtained a yield stress of 763 megapascals and maximum stress of 1042 megapascals. Below the fracture zones, pores of 90 micrometers were found. Tensile tests carried out at 650 degrees Celsius, obtaining a yield strength of 657 megapascals and maximum stress of 806 megapascals. Below the fracture zones, pores of 150 micrometers were found. Creep tests were performed at 650 degrees Celsius with a constant stress 322 megapascals and a rupture time of 45 hours was obtained. In the fracture zones, pores of 470 micrometers were found and microcracks are shown below the fracture zones. The porosity distribution and SEM imaging are added to the mechanical curves. The porosity distribution shows an increase in diameter size from 80 micrometers in AP condition to 150 micrometers in tension test at 650 degrees Celsius. Also, an increment in the number of pores for 150 in AP condition to 8,453 in the creep test at 650 degrees Celsius. Conclusions. Computer tomography coupled with SEM images allows for the determination of porosity, which is a term acts as a stress concentration and promotes the formation of cracks. An increase in pore size of 522 percentage was found in the creep test with respect to the tension test at room temperature, as well as an increase of 511 percentage in a number of pores in the creep test with respect to the tension test at 650 degrees Celsius. Additional research is ongoing to determine the evolution of pores during the failure for the shape and quantity of pores. Thanks a lot, Marco.